Thank you very much, and hello, everyone. So first of all, I thank you for the invitation to talk about my work during your workshop. And in this talk, I will try to focus on why it is important to detect the diffuse supernova neutrino background in all flavors. And also try to show that the large-scale existing and also the future direct matter detectors can help us to make significant steps toward achieving that goal. And I will start briefly with the supernovae because you all were how they work and also were very nicely reminded by Geo, Kirana, and Maniprata. So core collapse supernovae are very efficient neutrino factories, one of the most efficient in our universe. And they are deaths of very massive stars. So once this massive star tends toward the end of its life, it will run out of its fuel at some point and then can start collapsing under gravitational pull. And in this process, a numerous amount of neutrinos is emitted through the electron capture and also other thermal processes. And once in the core, the saturation density is reached, then it can bounce back and initiate a shock wave, which can then possibly drive the supernova explosion. So neutrinos in the core collapse processes are numerously produced. And also they basically carry pieces of information about the deep interior structure of this collapsing core. And besides that, in case of the so-called failed supernovae, when the star directly collapses to a black hole, they might be the only messengers we can see. So then detection of these neutrinos from a nearby collapse give us a very nice opportunity to probe physics in conditions that are not directly accessible on the Earth. In addition, if we are lucky enough and we will be able to detect these neutrinos not only in the more standard neutrino detectors like Super K or IceCube, but also in the direct dark matter detectors by the coherent elastic neutrino nucleus scattering, we will have very good multi-channel and large statistics detection. Then this multi-channel detection can help us to understand some of the more astrophysical unknowns, like, for example, the explosion mechanism and also yields of heavy elements produced in the star, but also could possibly tell us something more about the compact object formation. In addition, this could also tell us something about more of the particle physics unknowns, like what is the neutrino flavor evolution in the dense environments, but possibly could also give us hints or ways to better constrain some of the non-standard physics scenarios. So why we want to focus on a single rare event? And we know that core collapse supernovae in our galaxy and nearby are occurring rather rarely. So while we will have the large statistics and very nice detection, then it will give us information only about a single progenitor. And in case of that, from the theoretical point of view, from the other progenitors, we expect that there is not a lot of differences, but the nature may surprise us in the end. So in order to fully understand the whole supernova population, we need to measure multiple events. And to do so, we have to focus on larger distances, which directly mean that our fluxes are lower. So this is basically what the diffuse supernova neutrino background is. It's an isotropic and stationary flux of neutrinos coming to us from all the past core collapse supernovae in our universe. So in that case, as contrary to the galactic or nearby supernova, there is no need to wait for another 50 or 30 or maybe less if we are lucky years. We just need to have a good enough detector and detect this flux. And here, this equation here is telling us that the diffuse supernova neutrino background basically should depend on some of the astrophysical unknowns, like the cosmological supernova rate, or what is exactly the fractional black hole from progenitors. But it's also telling us that it should depend on more of the properties or the progenitor and what happens inside of it. Like, as I mentioned before, what is the neutrino flavor evolution in the dense medium, because as we heard from Irene, and also what is the equation of state or mass accretion rate, especially in black hole forming progenitors. But if there is any non-standard physics involved with that couples to neutrino sector, these flags basically should also possibly carry some information about it. So here I listed some examples of the possible beyond the standard model scenarios that could affect the diffuse supernova neutrino background. And we can have already scenarios that affect the neutrino spectra formation inside the star, like the key Vistera neutrinos, but also some non-standard mediators coupling to neutrinos, which don't necessarily have to couple only to neutrinos, but also to quarks or charged leptons that could affect the formation of the spectrum. But we can also imagine that some non-standard scenarios will also affect neutrinos that already form the flags as they travel towards the Earth. Like, for example, the neutrino decay or some secret neutrino interactions of DSNB neutrinos with other backgrounds, like, for example, the cosmic rare neutrino background. So with all that, if the new physics predominantly would couple to the X favor, so the mu and tau favors, it is kind of essential to know if this physics is there. It is essential to detect DSNB in all favors and to see if the new physics is there. So now I will move on to the limits on the DSNB. So on this figure here, you can see the most stringent current limits, which are on the anti-electron neutrino flavor. And here, all the experimental limits are shown as these colorful markers, and then the different theoretical modeling is shown as black, and then different line styles here. So as you can see, and as you already heard before, the most of the limits from the experiments are by a factor of 2 to 3 above most of the theoretical models. But with the current finished upgrade of superconductance to superconductance gadolinium, and also the Juno detector coming into place, the detection of the electron anti-neutrino component of the DSNB looks very optimistic. In addition, if we now move on to the electron component of the DSNB, we have the limit right now from the SNO detector that is about an order of magnitude worse only from the anti-electron neutrino favor. And in the future, it could be also possibly improved or maybe even detected by the Dune detector. So with the electron favors looking kind of optimistic, what about the X favor component of the DSNB? Can we possibly ever detect it? And if we just focus on this figure here, which shows the fluences, it kind of looks like it is maybe possible. So here we have the DSNB just for the X favors and also atmospheric and solar neutrino backgrounds. And it shows that there is still a detection window around 18 to 30 MeV. So if we would detect the X favor DSNB, that will be a quite huge achievement, because currently the more stringent upper limits are on order of 1,000 worse than the theoretical predictions. Then in our work with John and Irene, we try to see if by using the coherent elastic neutrino nucleus scattering channel, we can make some steps towards the detection of the DSNB. So here we can see what the Stevens process is. It's just basically when neutrino comes and coherently scatters of the whole nucleus. And this detection channel is very good for especially detecting X favors and also other neutrinos with especially X favors, because it is flavor insensitive and it has a very large cross section if we compare it with, for example, the regular inverse beta decay. In addition, the energy rate of DSNB is in the right energy range of the coherence of that reaction. So in order to try to see or constrain the DSMB with this detection channel, we focus on the detectors that could possibly in the future detect some of the astrophysical neutrino fluxes, like either the xenon-based detectors that already exist, such as xenon or Van, but also the future larger ones like Darwin and possibly Argo, and also some proposed Resnova detectors. So these detectors have already significant volumes, but will increase their volumes in the future, and we will have also longer exposures. They have heavy materials that can increase the cross-section by quite a lot, and also especially for the xenon detectors, because they are focused on the detection of dark matter, they are characterized by very low threshold already, and also have very low backgrounds. So here we can basically see how to calculate the event rates in these detectors for different neutrino fluxes. So now if we move on to the next slide, on the left-hand side, you can see the event rate per ton of ton-of-year exposure in a xenon-based detector. And here we can see that contrary to the just bare fluences, we no longer have any basically region where the DSMB is larger than atmospheric neutrino flux. And this is the answer to this is coming from the right figure, because if you see here, there is the differential cross-section plotted for different neutrino energies. And as we have a larger neutrino energy, we can produce larger recoils, but still the most favorable recoil is the low energy one, which means that basically the atmospheric neutrino flux was smeared over the DSMB toward lower energies, and then it overcame DSMB. So from here, it looks like the detection seems to be out of reach, but can we improve the limits on the X-favor component of the DSMB? And for that question, the answer seems to be yes, we can. And here, if we again look at the event rate, but now also convolve with the detector effects, we can see that basically still the DSMB is below the thresholds, below the backgrounds. But if we look at how DSMB scaled by a factor of 1,000, which is basically what current limits are, looks like it seems that we can put some limits that in this 7 detectors, basically that would improve the current limit by 1 or even 2 orders of magnitude. Then now you can see on these both plots how the limits on the DSMB X-favor component look like in xenon and then lead-based detectors if we just increase the normalization of the model DSMB flux. So here we can see that already with the current data from xenon 1 ton and also from X ton, we would get comparable limits to the super K limit. And in the future, as the detector sizes and also exposure are increased, we can get the limits that are only by a factor of around 10 worse than the current limit on the anti-electron neutrino flavor. So we also try to see how the sensitivity bounds on the X-favor DSMB change if we not only change the normalization of the DSMB flux, but also change the shape of the spectrum. So here we see how the limits look like if we assume that all supernovae basically emit the same Fermi-Dirac spectrum, which is characterized by the mean energy and then the total energy emitted in that flavor. So we again see that the largest exposure basically can reach the current limit of the DSMB anti-neutrino flavor, and even smaller, already like 100 ton exposures, can also be competitive in setting limits on the electron flavor component. So then this brings me to my conclusions, and I think it is safe to say that the anti-neutrino electron component of the DSMB soon will be detected by superconductor gallium and also Juno, and possibly other detectors in the future, where the electron neutrino flavor might be possibly detectable by June. And why we don't give yet the clear path to detect the X flavor, we showed that the 7 detectors that already exist can lead to comparable limits to the existing ones, but in the future they can improve these limits by up to even 2 orders of magnitude. So with these improved limits, we then will have kind of help from that side to rule out potential non-standard scenarios and also to better understand the supernova physics and whole supernova population. So thank you very much. I don't know if there are any questions, then please go ahead or comments.
First of all, thanks a lot, Anna. I can clap for everyone. So any question for Anna from the audience? Otherwise, I can. Okay, Georg has a question. So go ahead, Georg.
So sorry, just a very brief one. So the nu X on here, this is the heavy flavor neutrinos, or this is the sum of all the others? I mean, this coherent interaction is the sum of all of them, right? I mean, maybe I was missing it somehow.
So here we show the limits on one component of X, but assuming that the total X flavor is basically 4 times this X.
So maybe it's just a question of notation. So with nu X, you mean the heavy flavor, the nu mu and nu tau and whatever? And
no, I mean a single flavor, like either nu mu or nu tau.
Yes, but when you make a measurement of the coherent rate, then that will measure the sum of everything, the nu bar and everything else, right? So I was a little bit confused about how you separate the nu X from the nu mi and nu bar. I must have missed it to talk.
So here in our paper, we only assume that we set the limits by looking at the increase in the X flavor. And this is basically because if we look at the exposures, maybe this, I don't know which one it is. Maybe this one, because so if we focus on the exposures up to like around 100 tonoyears, we can see that the limits on the electron and also anti-electron are already much lower than these limits. So only starting at 100 tonoyears, then we need to include in our modeling also the electron flavors, and then at even larger exposures, we will need to include the nu bar.
And a slightly related question to this, if I may.
Sure.
So when the neutrinos come from far away, they must have decohered, and we should think about them as mass eigenstates, right? When the DSMB arrives at the Earth, we should think of mass eigenstates, sort of X and E flavors. So what you mean as of the back projections on the flavor, presumably, is this how this is to be understood?
Yes.
I mean, what arrives is something like an M1 flux, M2 flux, M3 flux, and the anti.
Yes, so these are the back projections on the flavors.
Okay.
Which, yes.
It probably makes no big difference, but just as a clarification. Thank you very much.
Any further question for Anna? Otherwise, I have a quick one, but it's just probably a stupid one. But just a curiosity, maybe you thought about this, but I always wondered, and I think that I've talked also to Lard about this, like when we think about the diffuse neutrino background, we of course focus on core collapse supernovae because we know that we produce a lot of neutrinos there, right? Do we expect also some neutrinos and some background of neutrinos from supernova type 1 and other type of supernova that are anyway like very violent and stuff even?
Yes, I think you also expect that, but the flux is lower And
Yeah, that's for
it's lower in the normalization and also lower in the energy, like the mean energy of the spectrum. So I don't
there is
think
no hope for that.
Right now probably not. Maybe sometime in the future if we could measure like keV scale neutrinos with a keV to MeV, like 1-ish MeV range. I think for a few that would.
So the energy, the energy there, even if it is like, you know, this white dwarf like accretion, the energy will be always set by like keV, so like temperature and typical energy of the white dwarf and stuff there.
So I think you have both the thermal emission and also the emission from nuclear processes that happened. So I think it will be like keV up to MeV range.
Okay, thanks. So, okay, I don't see any further questions. So I think that we can wrap it up for today. And we thank all the speakers. And we reconvene tomorrow with another exciting day in which we will have Francesco Calore, Sasha Filipov, Ben Safdie in the first session, and then Josh Foster and Sam Withy for the afternoon, let's say, or like post-break. So thanks everyone for staying here so late, or like whatever time it is for you, and see you all tomorrow.